Então, vamos começar. Oh, I was already starting in Portuguese. So, we are going back to English now. We will start now the closing keynote address. It will be presented to us by Professor Dani Gamerman. Dani did a BSc in Mechanical Engineering in '80. It was the year that I was born, so it was long ago, I guess, right? He did a master in statistics at IMPA in Rio de Janeiro, and then he did a PhD at the University of Warwick in '87. He has been full professor at Federal University of Rio de Janeiro since '96. He is doing a lot of research. He has been CNPq researcher since '87, so for a very long time. He has published several books, many articles in top journals. He has given many talks everywhere in the world. He is associate editor of Envirometrics, International Statistical Review, Statistical Modeling, Brazilian Journal of Probability and Statistics, so very good journals. So he has been very active in the community. And it is a great pleasure for me to introduce him and for us to have him here today with us. He's going to talk about his experience on applied statistics and from his career, I guess. So then, floor is yours.
Thank you very much. I will try to be brief. As you have seen, I'm not very successful at that, but I'll try to. I just should point out that after Janero's contribution, I think she should be delivering the closing address, and I hope she can do that in the next few years. She'll be invited to give closing addresses of many statistical meetings. But okay, let's not talk about this issue about data science, otherwise I'll spend easily 1 hour on that. I'm very happy to be here again. I have very close connections with Salvador and with this department. I visited this department many, many times. Some of them before most of you were born. So you should bear with me with that. The title is supposed to be a little bit provoking in a sense that I think we need, as you probably saw from my contribution earlier, we need to make some changes on how statistics is done, especially in academia in Brazil. And this is an effort towards how I think is one of the ways of moving forward. Okay? So this is the title. The title is supposed to be leading you to think more on how should I approach the profession that I chose. Okay? The slides are in Portuguese, but I'll be delivering the talk in English. But if you want to stop me for any reason, please do. Not so many times because we're already well behind schedule. The title could have been complemented by being an applied statistician in the 21st century, or even seeming to be a theoretical statistician. And I'm forcing my hand as much as I can to make you think of me as an applied statistician. I hope I'm successful. As I said, the prime role of the statistician is to analyze data. That's what statisticians do. And we don't analyze data for the sake of analyzing data. We're just trying to do that and trying to extract truths, in the plural, about the underlying feature that is expressed in the data. That's what we do. And the basic income for our work is data. In fact, I should have said information. Data is one of the guises that information comes to us. Or you can think of data in a more general sense. Any information that we receive is data. Okay? And this idea is getting more accepted, that data is not just numbers, it's many other things. is sentences, is maps, is objects. All these are data. And we get data when you need to know how to look at the data, which looks easy when you read it, but it's very complicated, as I think we are getting more and more familiar with the adventure of big data sets. And the way I'm going to approach the problem of looking at the data and uncover truth is through statistical models. That's not the only way of doing it, but I think this is the best way of doing it. And I will try to convince you of that through practical example, not through theorems. I'm going to illustrate those ideas with some of my recent work. I'll be presenting you basically graphs, figures, and maps, and tables. That's all I'm going to do. Okay? And for each application, I'm going to show you only 3 applications. Let me put some. Let me know when I'm getting close to 12:30. Let me leave it there. I will be restricting the details, the technical details, to a single slide. Okay? So let's go forward. The first of the 3 applications I'm going to show you is a study that I was involved with, people from medicine. This was part of a PhD in cardiology and a PhD in statistics. So we got 2 PhDs out of a paper. It was a brilliant effort. The paper was published in a journal called Statistics in Medicine, because that's what we were doing. That's exactly what we were doing. And it has to do with understanding what are the main elements affecting death by cardiac disease. So the data we analyzed, the main input, as I was telling you, is represented there. There is the data. The data is a collection of, this is a map. This is a map of Rio, of municipality of Rio. And you can see red patches. It's not really a patch. We have 18,237 dots on this map. Okay? And some of them are so close together that they become a patch. And each dot is the place where somebody who died from cerebral vascular disease between 2002 and 2007. Okay? It's the home of somebody who died from this disease. Okay? It's an important disease, as you can see, many people died from it. And I plotted it. On this map of Rio, you can also see in thick lines the division, the administrative division of the municipality of Rio in 33 administrative regions. Probably Salvador has something similar. And also in thinner lines, we have the division of boroughs. We have 160 boroughs. Each borough is contained in one of the 33 administrative regions. So these are the division of the city for administration purposes. Of course, takes into account other features, but it's basically administrative division. But this is important for what we are going to do next. The point I'd like to make, it's not clear from this picture, but as you can see, let me show you. This is this part of Rio. There's a thick, it's a red cover, basically. You don't see points, you just see a red patch, which may lead you to believe that this is not a good place to live if you want to survive from cerebrovascular disease. But these are the richest parts of Rio. That's where it's understood to be nicer to live. It's where it's most expensive to live. It's in Leblon, Ipanema, Copacabana. This is so covered, so many people die there because there are so many people living there. The demography is completely dominating this picture, and we should be aware of that. Of course, most epidemiological studies such as this take that into account, but it's important to point out for those who are not familiar with epidemiological studies. It's vital to take demographic features into account. So, for example, why is it empty here if it's so covered in red? Because here is a chain of mountains and nobody lives there. Why is it empty here? Because it's so thickly populated here. Why isn't anybody living there? Because it's a lake. Nobody lives in the lake. And so forth. Okay? And here it's the airport, and here is the university campus. Okay, well, some people here have studied. Okay, so we want to understand what makes red dots appearing here and not here, of course, after taking account demography. We need to standardize because of their demographic effects. Okay? So, the statistical analysis that we are going to perform is based on a discretization, which is fine in this setting because the purpose of this study is to provide elements for the health secretary of the city, which doesn't work on a house-by-house basis. They work on a regional basis. So for them, it's okay to know what happens in a borough at most. They are not even going to use the information about a borough. They work on administrative regions and they allocate resources according to the administrative regions. So discretization is not really an issue there. But I'll go back towards the end of my talk about the issue of discretization. Okay, but this analysis I'm going to present is based on the discretization, and the intensity of death is written as a function of explanatory variables, like in your standard regression, nothing new. We have information about age, gender, level of education, and marital status of each individual. And we are also taking into account the socioeconomic level of each region. In this case, we take the IDH, which is an index compiled by the United Nations that sort of inform what is the socioeconomic status of any region. Okay? If this IDH were able to handle all the effect of disparity associated with space, then all the other effects will be constant. Like in your standard regression, you will have a single coefficient to explain the intercept, the regression coefficients of all the explanatory variables. Okay? And this is, I'm not complaining about this index. This index is good. It explains the level of wealth in a given region, but as you'll see, it's very far from enough to explain the disparity. That's where our models came into play. And this is a technical detail slide. Basically, it's a point process observation that we're having. Is just a collection of occurrences over space. So each point process, we are taking as simple as possible model, which is the Poisson process, with an intensity lambda, capital lambda, and the intensity is divided into two parts. One, which I'm denoting by R, is an offset, is known, is a populational density to take away the demography from our analysis. And this small case lambda is the true intensity that we want to evaluate, which is larger, which is smaller. Okay, so this intensity after a log transformation is explained through covariates. So let's concentrate on this one first. This is the effect that we are familiar with. It's a regression coefficient, Z transpose times beta. Okay? It's a standard regression that we are all used to. We have an intercept that must change with space, that must be allowed to vary over space to account for differences that were not captured by this covariate. And there is also, and this is a novelty, if you like, of our approach, also this regression coefficient associated with these explanatory variables associated with each individual. Okay, so V is the age, gender, level of education, and marital status of an individual, and some interaction terms as well. Okay, and alpha is its coefficient, and we are used to coefficients that are fixed. And in this approach, we are allowing the coefficient also, not only the intercept, but we are also allowing the coefficient to vary over space. Okay, to account for whatever heterogeneity is observed in the data. Okay. Okay, so the model is completed by imposing some structure over the intercept and over the regression coefficients. They both are described as Gaussian processes, which means that you expect regression coefficients of neighboring regions to behave similarly, and you expect neighboring regions of far apart regions to not behave similarly. Okay? That's the basic idea of the approach. So we are allowing the regression coefficients to vary over space, but they do not vary independently. They have a structure relating them. If you put this variance or this precision to 0, we are back to your standard regression where alphas are all the same. They don't vary over space. Okay? That's it. Results. We did all the analysis, and this is the result. This is the coefficient of age. Age, we all know, it's an important explanatory variable for diseases, especially for this kind of disease. As we get older, we get a higher chance of getting cardiovascular problems. All of us will. Okay? And as you can see, the effects are all positive. This is 0, all positive, meaning that age increases your chance of death. Okay? There's nothing new there. We all knew that. But the important point is that by how much? That's an issue that is important, especially for the epidemiologists. They want to come up with numbers saying how much more likely you are to die because you have gone older. Okay? Now, your standard regression model would lead to this dotted line. It's shaded, very thinly shaded area, which is the value of the estimate, the point estimate of the regression coefficient with uncertainty bounds. Okay? So it's very precise, the estimation. You cannot even see the shaded area. It's very well estimated, very precisely estimated result because it's based on a lot of information. I have 18,000 people. That's a lot. That's why the model is so certain about this effect. And the effect is around here. Okay? Now, what you see, these lines, they are the estimates of the regression coefficients associated with each of the 33 administrative regions of Rio. And alongside, the red dot is the point estimate, and the bar is the uncertainty bounds for each of the 33 estimates. And as you can see, they vary, and they vary a lot. Okay? Which is, to me, a very, not only vary a lot, they vary a lot, and the variation is significant. As you can see, the richest, the wealthiest regions, which are these 4 regions, are completely different. The estimates of the regression coefficient is completely different from the regression coefficients of these regions, for example. Those are now well above the fixed effect, and those are well below the fixed effect, showing that there are significant differences on the effect of age on your chances of dying. Okay? This for me is already enough evidence that we need to allow for variation of the effects of the regression coefficients, at least the regression coefficient of age. We got similar results for the other regression coefficients as well. But age is, of course, the most important for this disease. Okay? The lowest value, the value where the region where age is less important, how old you are is less important, is at a slump down. Which may lead you to believe that If you are getting older, you better move to a slum town and live there because your chances of dying are going to be smaller. Wait a few minutes and I'll show you why you shouldn't do that. In case you don't know yet why you shouldn't do that. We can put the same numbers in terms of relative risk, which is something that epidemiologists and doctors like to see. And the chances range from an increase of 50% in some town to 270% in the richest regions of the city. So it's a big difference. As we have already seen, this picture is basically the same as the other one. Okay? And the fixed effect is lying somewhere in between them. Okay? Missing entirely the picture, basically.
Dani, o risco relativo você pega cada componente aleatório dividido pelo componente fixo, é isso?
Now, okay, let me be more precise. This is a good question. I didn't explain. I'm worried about the timing, so I'm not explaining well. This is the relative risk for each region, meaning I'm comparing somebody with an X years of age against somebody in the same region with X plus 10 years of age.
Okay.
Okay? I'm comparing, I'm fixing everything, including the region where the person is living. Everything else is the same, I'm only changing age. Okay? This is important because I'm going to do other comparisons soon. Okay? So the other individual covariates show also substantial variation, but not as impressive as age. I'll show them. Which is again more evidence in favor of this spatially varying effects model. And this is all done despite the highly significant coefficient of IDH. This Human Development Index plays an important role in explaining the spatial differences, but not enough. We need something else. Okay? Also, as a result, the fit of this, we took DIC criteria for, it's just one criteria, and it favors the model with space varying regression coefficients. Okay, but for me the most impressive is the result that we obtained from the analysis, showing significant differences between the uncertainty bounds themselves. That's another comparison. This is a comparison of, so let me explain to you. I'm taking the protective configuration. What is a protective configuration? It's the best possible configuration you can have in terms of your individual characteristics. It's to be a woman, be young, living with somebody, and with high education, high inverted commas. Okay, so think of this person and now put her in the wealthiest region, in Leblon. Pick this person and put her in Leblon. And let's have a look at the risk of her dying. And we are going to compare this woman against the same woman, or the woman with the same characteristics, but living in the other 32 regions. And let's see how much the risk increases. And as you can see, the risk increases. Now, you cannot see, but I can tell you these numbers will go all the way up to, I don't know, around 14. So the risk increased up to 14 times for this person as she moves from where she is living in the wealthiest region and moves to other regions. Okay? And then, now you can see what happens if you live in a slum town. The slum towns in this map are the ones with the darkest color. Those are the highest relative risks.
I never lost it. So you moved someone to CSDS experimentally? Or
No.
Just hypothetical.
The data, I should have explained that also. We should explain, this is another serious mistake I made. The data, our data, was a pile of 18,200, well, it was a bit more, but let's put 18,000 death certificates. That's our data. People are dead already. Okay? We just analyze where they live and what the personal information contained in the death certificate of each
someone
person.
that was living here, then in a part of his life he moved to another
No,
place.
no, no. They died. They are dead.
Yeah, but you have the information of his life.
No. We only have... Have you seen a death certificate in your life? You haven't. Good for you. Unfortunately, I have seen a death certificate. It doesn't include where you have been living in your life. It just says where you were living when you died. Okay? That's the information. I'm comparing this person, this hypothetical person, against another hypothetical person, which is also female, also young, also living in somebody, also with high education, but living in a different region. Okay?
And this strategy to identify these comparisons is like is randomized around the city, or you stated some rule to compare this person and this another person with 10 years.
Well, there are, as you probably is guessing right, there are many possible comparisons. I made two only. There are billions of comparisons no one could make. I made two comparisons. The previous one is a comparison between two people in the same region, only differing in age. Okay? Now, this comparison is two people with the same individual characteristics, but only differing in where they live. Okay? So, if I look here, what is this? I think this is Rocinha. If you look in Rocinha, I'm comparing this woman living in Leblon with this same woman, the same characteristic living in Rocinha. And the woman living in Rocinha has 14 times higher risk of dying from cerebrovascular disease than the woman in Leblon. Okay? So these are the main slum towns: Rocinha, Cidade de Deus, Alemão, what else? Some other slum towns, okay? They appear and they show that they are important and they are bad for your health, okay? They're not a cause of health, but living there is a surrogate information that your health is going to be much worse than the health of somebody who is wealthier, okay? Just another example, this is the effect of level of education. We did the analysis with boroughs in terms of administrative regions and the effects. If you do analysis by borough, which are those lines, it's much more blurred. Apparently, there's no effect, which seems to indicate that we'd better doing the analysis by discretization over administrative regions than over boroughs. Let me just put it as such for this moment. We go to the second example. I have this and another example more to go. So the second example is work that we have developed with Fernando Nascimento, who was a PhD student of mine, jointly supervised with Edilberto Lopes, who gave a talk here yesterday. The main idea of his thesis was published in a paper in Statistics and Computing, and this application specifically is the application that was published more recently in a journal called Test in 2016, and it has to do with the time movement of extremes. Okay, so this is a plot of the absolute return of the stock of Petrobras. Okay, the return is the difference between what is the value of the stock today divided by the value of the stock yesterday. Okay, that's the return, and it can go higher or lower, but we are taking the absolute value. Okay. And this is the plot of the returns. They're basically very small in absolute value, but sometimes they spike. And that's what the importance of the study of stocks in the financial market, to see what causes, what makes, and how it behaves. The occurrences of spikes. Usually they are associated with periods of financial crisis or financial instability. Okay? And it's more important to analyze these spikes because this is where you get big gains or big losses. This is where fortunes are made and they are lost also in the financial market. It's on these moments. So one question of interest to us was, is there a limit for the return, for the absolute return? Could it have gone, at least theoretically, all the way to infinity? That's one question. Can we quantify the probability of a crisis, of a financial crisis? This is another question that we would like to address. Okay? Okay? I'm going to the technical slide now. The technical slide is not so bad. There is a theory that governs studies associated with extremes. I'm not going to bother you with details, but basically because I'm going to have a lot more time tomorrow and the day after tomorrow to talk about this in details in the short course that are going to happen over extremes. I just want to point out for this moment that we use the standard approach to the tail, which is using a theoretically justified distribution, which is denoted by GPD, generalized Pareto distribution, which depends on a couple of parameters, the scale parameter and the shape parameter, controlling the shape of the tail. And what we did in our analysis was to allow the scale to be fixed, but allow the shape to vary over time. Okay? But to vary over time, again, not in a completely random matter. We're not assuming the shape parameters to be independent, but we are going to allow, after a transformation, we are going to allow the shape parameters to vary in a structured way by saying that the shape of the distribution of the tail today is a function of the shape of the distribution yesterday. Okay? Things are related in time, and that's what we are expressing here. And these are the results. This is a very rich slide, and I need to spend a few minutes on it. Okay, first, this is the raw data. Okay, the same data we had before is here. Just a scale, we just changed the scale. Now, this line here, can you see this full line going all the way to the end, is the posterior estimate of the 99.9999 quantile. Everybody knows what a quantile is. It's a point above which there is a certain probability, which in this case, above this quantile, there is a 0.0001% probability of being larger than it. Okay? This is the map, and it changes over time. As you can see, that model allows us to see that there is substantial change over this quantile. Also, on top of this plot, there is another plot that is broken. Can you see? The plot is broken. The plot is only appearing in the shaded area. It doesn't like the sun. It's only protected in the shade. And this plot is the plot of the maximum, the theoretical maximum of the GPD, of the distribution that is governing the extremes. It exists for some periods and does not exist for other periods. The GPD is a very rich family of distribution that contains a finite limit and also an infinite limit. Okay? And that's what we are getting. Sometimes, literally sometimes, the limit is finite, and sometimes the limit is infinite. For example, here, the limit is infinite. Here as well. Okay? What is left to explain is the shaded area. This is the same picture again. The shaded area, do I mention what the shaded? The shaded area is basically, the shaded area basically is providing at any given time the probability that the limit of the distribution is finite. So for instance, on this time here, there's probability 1 that the limit is finite. On this time, we'll take this time. On this time here, around January 2004, the probability that the limit is finite is 0.6, 60%. Okay? But for instance, in this whole period here, around the 2008 crisis, basically it's cut, but there's no, the probability is 0 that the limit is finite. The theoretical probability that approaches that represents better what's happening there is that the limit of the theoretical distribution that is explained in the extremes is infinite. Okay, so that could be, if you like, a definition of a crisis, of a financial crisis, having an infinite limit for the distribution of the tail. If the tail could be infinite, it could be one way to define, mathematically define crisis, financial crisis. Okay? And the third example that I would like to tell you about is work on the effect of pollution on health. It's joint work with two Italian collaborators, Luigi Politi and Pasquale Valentini. The basic ideas in a simpler model were published in 2012, and we are still struggling with the publication of this one, and I think we will see why the referees are getting edgy about it. Let me explain to you what's going on. So, the problem is well known. Is pollution affecting health? That's a very typical question that I believe almost all of you have heard. And maybe some of you have already worked on. Okay, so that's what we are going to. So, and again, you see the question is pollution affecting health? That's a typical regression question. Is X affecting Y? That's our approach to the problem. That's the approach most people take. But we want to do it in a more detailed way. So our response, Y, is the number of people that are hospitalized. And we took only old people and only two diseases, respiratory diseases and cardiac diseases. So we have measurements of the number of hospitalizations for two diseases daily. Okay? And we would like to explain Y by X, like in any regression. Okay? Which is measurements of the pollutants. In this case, we have 4 pollutants. Okay? The usual pollutants are those. There are many more, but these are the usual ones. Okay, so what we would like to do is to regress X on Y, or Y on X. The problem is that we cannot do that. And we cannot do that because there are other important variables that cannot be disregarded. These are usually known as confounders. And we have confounders here as well that we need to take into account, which is basically climatic information. Temperature and humidity. They are some surrogate information about the climate, and they must be included in the model. People working in this area know about it. It's no surprise for those of you who have done some work. So we need to have that into account. So anyway, that would be our canonical representation of a regression. We have X affecting Y. We have confounders affecting the pollutants, but we have the confounders, the climatic variables, also affecting the outcome. There are a few regressions there. To understand what we did, I would like to ask you to forget about Z and just think about X and Y. As you see, it's complicated enough as it is on its own. That's the region that we took to analyze. The region of northwestern Italy, the regions of Piemonte, which capital is Torino, and the region of Lombardia, which capital is Milan. Okay? Around here. And this is probably the border here. And those are the administrative regions. Just like in Rio, health data is usually collected over administrative regions. Okay? And the dots are places where there is a monitoring station, monitoring pollution. As you can see, there are many monitoring stations in this region and in this region because it's where people mostly populated regions. Okay? The first problem to notice is that we are trying to explain measurements based on regions through measurements that are based on locations, not on regions. How do we associate one? How do we associate one with the other? There are many ad hoc procedures that can be used, and people have done that to analyze. For example, they just say that to explain the mobility here, they use just the measurements from this region, which is a very crude way to approach the problem. But the problem is complicated. This misalignment poses a difficult scientific problem. Okay? Another approach that has been used a lot is aggregation. Forget that there is space, forget to have spatial information, and just aggregate and do a temporal analysis. We don't want to do any of these two. We don't want to oversimplify the data, and we want to oversimplify the model. But before that, let's take into account the dimensions that we are handling here. The response contains two measurements for each of the 28 health administrative regions of Italy over 365 days. Because we chose to analyze just 1 year. We could have analyzed more years. So our data, the data we are trying to explain has 2,000 numbers, 20,000 numbers, sorry. The explanatory variables, remember we had 4 pollutant measurements made over 365 days. The first pollutant has 95 monitoring stations, the other one has 168 and so forth. So we have 165,000 numbers trying to explain these 20,000 numbers. It's a lot, okay? And now we have the confounders as well. So the canonical model that try to address the issue directly from the whole bag of pollutant measurements into the whole bag of mobility counts is not going to work. There's far too many parameters in these regression models for it to work. Even without taking into account the fact that we probably need to include lagged effects as well. So it's undoable. Okay? If you have a huge machine, probably you can do that. But you end up getting lots of non-significant parameters because you're building a model that's far richer than you have to use. Okay? So you cannot work, basically. Even if you have a computer and computational resources to do it, you shouldn't do it. So our approach to the problem, as I said, there are many ways to simplify the dimensions involved in the model, not on the data. Well, maybe by simplifying the data, by aggregating. We didn't do that. What we try to do is to, instead of approaching the problem directly, we use factor analysis. We all are familiar with factor models, and we chose factors for representing mobility and factors to represent pollution. And we build a regression model at this latent level of the factors. We build a regression between the factors associated with pollution and the factors associated with mobility. And when we do that, it's not that difficult to find out that there is a lot of correlation between the measurements, and you can simplify the dimension dramatically. The dimensions go down a lot from the dimensions of your original data set. And then you end up with a regression which is much more concentrated after factorial models. So we have, and these factors need to be dynamic. As I mentioned to you, it's well known the effects are not contemporaneous. There is a temporal effect that is relevant for this specific application, and this should be taken into account. The one point I'd like to make is that the factor approach applied to this setting simply solves the problem of misalignment. The spatial misalignment completely disappears because we have spaceless factors. The factors are not associated with space. The weights of the factors are associated with space, but the factors themselves are not. Okay, so you can build a regression of the factors which don't have spatial orientation, so the misalignment disappears. And the model is built with transfer response functions that are models, multivariate transfer response models that are usually frequently common in time series literature. There are a number of choices that we have to make. We have to decide the number of factors, the order of the lag effects. All those things must be taken into account or must be chosen according to some optimality criteria, fit criteria, or whatever. Okay? So this is a technical detail slide. Let me just go briefly to that. We basically assume that the mobility counts, Y, and the pollution measurements, X, are all coming from the same families of distribution, F, denoted by F, Y, F, X, which have some dispersion parameter, could have other parameters, doesn't matter too much, and some mean parameters. And those mean parameters are the parameters that we're going to build our regression on. We could we have built regression over dispersion parameters? Yes, we could. But it's already complicated as it is by building it over the mean. Okay? So what we do then is to use what anybody who has done generalized linear models is familiar with, do some transformation of the mean parameters, and then we have a model which has some mean coefficient, which is probably where you put your regression coefficients, your regression components of the factors, observed factors that you know about, but also has a component associated with the factors that explain the variation and represent the heterogeneity that you don't know about. Okay? And we have a number of factors, M and R, which are much smaller than the original dimension of the data, typically. And then each of the factors is autoregressive on its own. The factors associated with the pollutants is autoregressive, strictly autoregressive. The factors associated with the mobility is autoregressive, but also embeds into its explanation the factors, which could also be lagged, of the pollutions. Okay? So, as you can see, we could make this model richer, but it's already complicated enough. And we have too many parameters. These coefficients, these regression coefficients, are all matrices. And so you may need to even, again, force some of them to be zero as much as possible. And there are many ways of doing that. We did in one particular way. So in the end, we end up with pictures like these. These are the response, impulse response functions, which are the function associated and how much the outcome from a specific disease in a particular administrative region varies over time as we give an impulse of one unit to each of the factors. Remember, we'll be doing everything over factors. So I have we ended up choosing 4 pollution factors. Nothing to do with the fact that we had 4 pollutants, because they are, each of the 4 factors are a mixture of the 4 pollutants. Okay, so for an input of 1 unit, and we know how much that means because we know how we build the factor from the original observation, so we can tell you what kind of average is that of the different pollutants. For an input of 1 unit in each of the 4 factors associated with pollution, what is the expected outcome in the mean of the mobility counts in a specific region, in this case Milano 1. Okay, and as you can see, the effect, as expected, goes up and then goes down. There is some uncertainty bound also associated in this picture. So the first factor is basically significant. The move is basically away from zero around this region, which seems to indicate that is happening what we expect, that if you have an impulse of pollution, you would expect people not to become sick exactly the same time, but it takes a few days. In this case, it takes around 3-4 days to reach the peak of the effect of the pollution, and then it dies down again. Okay? So you can get this picture. For instance, on this one, there's not strong indication of any effect associated with the third factor, or even the fourth. There is some indication of some effect similar to that, to the observed for the first factor in the second factor. We can do the same picture for any other region. This is another example. This is Torino 5, another region in the city of Torino, and you can see that the effect now is much more squashed towards zero. It's not so strong in that region as it was for Milan. Okay? We can, in this analysis, in fact, we left a few, 10 days out of the analysis. We did all the analysis. We did the fit of the whole data set of 355 days and left 10 remaining days for prediction, out of sample prediction. What's the word for the validation and testing and I always forget the name. Anyway, it's for prediction. Okay, I will use the statistics. I'm still not used to this machine learning name. Anyway, so this is the prediction out of sample, and you can see they are all inside. This is the data. Okay, these are 4 different regions. Okay, this is the mobility count for cardiac disease of hospitalizations, and this is the prediction. And this is the 95 credibility interval. This one is not so nice, but it's still inside the credibility interval. And this one seems to following the data well, and this one also not so nice. We do similar things for respiratory diseases, like a little bit better, the predictions in this setting. Okay? So it seems to be doing a decent job, our models. If you have studied factor models, you know that one of the most important features of the factor models is not the factors themselves, it's the loading associated with the factors. Those are the features of the factor analysis that you use to interpret the factors and give them names and some sort. So these are the loadings associated of the single factor in this case that we use for respiratory disease, again for cardiac disease, and this can be brought to the specialist and he will be able to interpret them. For instance, this is a more obvious factor to interpret. As you can see, this factor is pretty much oriented towards darker, which means I cannot see the picture well. Higher values of the loading. So this first factor associated to PM10 seems to be an indication of the effect of the metropolitan region of Milan, basically. Okay, because that's where the higher loadings are located. Okay, and the same things could be done. The same things could be done for many other regions, and we have all that done in the paper. Okay, I'm approaching the end of my talk. I just want to go back to the first example. Remember the first example that I presented you about the mortality in the city of Rio, and we were discussing about how to discretize. And in that example, we're fortunate that we have a discretization structure ready for us, provided by the administrative health regions. So it was the data, the setting where the data was collected led us to a satisfactory specification of a discretization grid. Not always we have that. And in principle, a point process analysis should be done over the continuous space, not over the discretized space. So discretized space, in a way, is a simplification of the model. Okay? So that applied work that we did with doctors led us to a development that was not so applied. But that's okay, it's not a sin. And then, after bringing it to a colleague, we did some work, we thought about it a lot, and then we came up with a solution. Solution well received, was published this year in Series B, and basically shows shows us how we can perform the analysis without any approximation. Without any approximation in inverted comma. Apart from the MCMC that we have to use in the end. But we are not approximating the model, we are approximating the distribution from which we are sampling from. And that we have a very good control over it. We know how good this approximation is. But the model is not approximated. And most approaches to point process, even in the simple point process specification, using a Poisson assumption, need to have an approximation in the model, which is something that we wanted to avoid. But this only came about, this theoretical development only came about because I was worried about an applied problem. And the applied problem led us to think and think hard about an issue and led us to come up with a theoretical solution to the problem. Okay? And in the end, the technique we developed can be extended to time, which is something that we didn't do in that type of analysis, was fixed over time. We considered the time frame of 2002 to 2007 as a single time specification. We only have spatial effects. This technique also extends to continuous time, discrete time, covariates with regression coefficients that vary over space and time. All that can be included into this framework. The idea basically is lunchtime is well past lunchtime for me, but anyway, let me just show you briefly some of the technical data. There's a lot more. But basically what happens is that when you have a Poisson process with the intensity function lambda, your likelihood has this form. And there are two big problems in the likelihood. First of all, the parameter of interest, lambda, is a function. So you have an infinite amount of parameters to estimate. You need to estimate a function, which is not easy. Let me just simply put it this way. And even worse, the likelihood has an integral that nobody knows how to perform. Nobody knows how to evaluate this likelihood. Nobody. Not even us. Okay? So, this likelihood is undoable. You need to approximate it somehow. What we did was not to approximate. We did a data augmentation. There is an assumption. There's a price, but I think this price is very little. The price we have to pay is to assume the intensity function is bounded by a number. It's finite. If you do this data augmentation, then it's okay because the augmented likelihood, which some of you may be familiar with, I have no time to explain this now, but the augmented likelihood, as if you can look at it carefully, has no integral. The integral that was preventing us from doing an exact analysis is missing. So we can do an exact analysis. Even better than having the integral disappearing, it only depends on the intensity function. You see the intensity is function of this parameter beta, and there's only a finite number of betas. Okay, so just like in the discretization where we have a finite number of regression coefficients, here we also have a finite number, so we can perform the analysis. Basically, that's the basic idea of what we did. By doing that, I must say also that we didn't put a log transformation. The log transformation doesn't make sense anymore. The log transformation allows the intensity to go all the way to infinity. It's just used for convenience. So we use another convenient transformation is the probit transformation, which is also an increasing function, monotonically increasing, just like the log transformation. Okay, and this worked well for us, and we were able to perform the analysis there. Okay, so that's an application. This data set is not really relevant because the data set is available in R packages, in this case SPATStat, and over 300 people have published papers using this data set, so we were 301. So this data set is the intensity of oaks. Each dot is a place on a plot of land where an oak is present. Okay? And this, we're trying to estimate the intensity of occurrence of oaks in this region. So what we did is to discretize. That's the standard approach for approaching this problem, is to discretize, to put the discretization as fine as possible so that you can assume that you have reached a continuous or something arbitrarily close to the continuous. Okay? And that's the results that you can get by putting 1,600 regions, 10,000, 40,000. These are our estimates. The coloring is very important here, but it's basically around the same range. The range goes from 0 to 12, around 12, and we have the same. And it's funny to notice that our final result, contrary to what we would expect, it's much closer to the roughest of the discretization schemes, which the one with more plots than the one with the finer. As you go finer towards regions of size 0, we get further and further away from the model that from the result that we got. I must say that the models are not the same. So this picture is not supposed to be the limit of this, because this is using log Gaussian transformation, log Gaussian Cox processes, and this is sigmoidal transformation, or probit. Sigmoid is another of those words from the data scientists like. Probit transformation. So it's not exactly the same, but it has the same picture. It has to do something similar because we're analyzing the same data. Okay, but it's a different way. I think we are running out of time and getting a lot hungrier. So the conclusion, that is a single slide of conclusions, is that simple models are good basis. We started all my applications, the applications I showed, from thinking of simple models and trying to incorporate into the simple models features that were more adequately describing the data. And that's basically what I say. The single models are not enough to many of the analyses, the usual analysis that must be performed nowadays with the availability of richer data sets. There is a lot of sophistication in the data structure. You are well, after this workshop, Congress, after this Congress, you are, I think, well, better equipped of understanding what I mean by that. And there is a lot of statistical software available. And it is important, I would say fundamental, to be able to know how to look for the tools that may help you analyze your data set. It's probably there. And if it's not there, wait a few months or a few years, and it will be there in some R repository. Okay? So you don't need to be like me, wanting to develop, be one of those developing sophisticated tools to analyze sophisticated data. That's work that we in academia do, not work with people who are doing data analysis on a regular basis. But it helps a lot to know where that they might exist, they probably exist, and to know where to look for them. Finally, I'd like to thank my co-authors because they are the ones who bring me motivation to do what I do. with questions and queries. I'd like to thank the supporting agencies in Brazil that help me do what I do. And finally, the organization of this conference for giving me the opportunity to talk about my work to all of you. Thank you very much.
Thank you very much, Dani, for the very enlightening talk. We got a bit out of time, but we can make time for one or two quick questions, if there is any.
First of all, congrats for the work, it's very good. My question is about your first study in
Okay, go ahead.
ECVS.
Okay.
Okay, my question is, you evaluate how long time those people live in a neighborhood? I mean, imagine the following situation. I live my whole life in neighborhood A, right? At some point, I move from neighborhood B.
And you died the day before, the day after.
Exactly, one day after. My question is, which neighborhood I belong? Because in this case, the neighborhood is not the guilt of my dad, right? So, you know what I mean?
I know what you mean. It's a good question and I have no answer for it. We're just hoping that the change in neighborhood is not relevant for this study. People move. People don't move that much in Rio, I don't think. Certainly they don't move from Leblon to favela and from a favela to Leblon. There are a few. There are a few singers and football players, but they are minute proportion of the population of Brazil. But this is a problem. As I was explaining him, we need to data is our God. We need to pay a lot of respect for the data. And what we had for this analysis was a pile of death certificates. And they have a number of people who are, I wouldn't want to be in that position, who were compiling, transforming these death certificates into a table of numbers that we could analyze. When I arrived in the project, the file, the data file was already there. But you're absolutely right.
Because taking Brazil, right, people move, this corporation people move the bone for favela, is minimum, you know. But in another country, you move all the way for all the neighborhoods, you know. If I can apply this method.
No, you're right, yeah. I have nothing to say other than that this happens in all directions. And hopefully, it's very complicated to prove what I'm going to say. Hopefully, this is ancillary to what we are trying to measure. So, I mean, they don't all get rich or they don't all get poor. There is all kinds of movement, from middle to poor, from middle to rich, from rich to poor. And the movements are not associated with the pattern of that. But I wouldn't say that if there were just cardiologists in the room.
Okay, I think we can move on. If there are further questions or comments to Dani, I think he will be happy to discuss with you after. So please join me and thank Dani again. It was a pleasure to have you. We are moving now to the closing ceremony. I will just invite Lisander to come here to join me to close quickly. I promise it will not be more than 10 minutes. So, as many of you knew, we had a couple of awards for this conference. We had an award for the best paper and the best poster. And I would like to thank the jury that helped us to choose the winner. I would like to thank Edibert, Christian, Marco, and Magda, who helped us to select the winners. And we only have a certificate. You know, there is time of crisis, so there is no money. So only the certificate. So the best paper award is going for the paper entitled Voronoi Data Linkage, Extracting Data from Polygons to Points by Lucas Godoy. Congratulations.
Thank you.
And the best poster is going for the poster entitled Modeling High-Dimensional Time Series from Large-Scale Brain Networks, which was presented by Diego Nascimento. So now, very quickly, I was doing some counting to see which kind of people are here. So we had a little bit more than 100 participants in total. We had I think for some reason the 9 was a number of hours in this meeting. We had people from 9 different countries. We had people from 9 different Brazilian states. And we had 9 colleagues from our department attending. So I think the 9 was a kind of a number for us. So we had also a little bit more than around 60 contributions in total. And for instance, we also, as most of you know, we broadcast the keynote speeches on YouTube. For instance, the video where we broadcast the opening ceremony and the keynote lecture by Catherine already got 143 views, so I think it is quite useful. And we also had, for the first time that I have been in a conference, is the first time that I have a real politician attending the conference. So we are really happy that Dr. Acácio Coutinho was here with us. He's the mayor of Carlos Chagas in Minas Gerais. And it is great to see what they are doing in their local municipality, and this is really something interesting for those that attend the session. It was really something impressive. What else? We are going to send a survey today for all of you, so please share with us your views, and it will be like less than 5 minutes to answer that. Don't forget, this is the closing ceremony, but we are still going to have 2 courses in the afternoon. There is one course that will happen here, and the second one will happen in the FACON. So we'll have some in the map. You can see where it is, and if you have questions, you can ask us. So I'm going to talk on behalf of both of us, so that everyone can go to have lunch as soon as possible. So we would like also to thank all the speakers, the keynote speakers, the discussants, the speakers in invite sessions, the poster presenters, the presenters of contributed talks, and of course all the participants. It was really a great pleasure for us to have you here with us. And besides me, we also have another 9. I think for me is the most important 9, which is the local organizing committee. So I'd like to ask all the people in the local organizing committee to stand so that we can thank all of them together. Okay? So, Lisandra, Roberto, Gilberto, please stand. Lion, Alex, Jalmar, Mateus, Elizabeth and Talitha. So please join me and thank them because they did a marvelous job. So they are really the most important 9 that from all those 9 that I mentioned. And of course, everything that is so good as this ends very quickly. So thank you again all for coming. And these are the last words of this conference. So thank you very much, really.
Professor, é comigo? Eu procuro quem lá na faculdade. Eu procuro quem lá na faculdade. Eu não sabia que estava passando. Eu deixei o papo
Bom trabalho e boa sorte. Obrigado. Tá aqui.
Estou a ver, está aqui enrolado. É este aqui.